Hello, welcome back to Stars, Cells, and God. I'm Jeff Zweerink, and I'm joined today by Dr. Kevin Birdwell, and we're going to be discussing the winter gatekeeper hypothesis. Kevin, good to have you back in the studio again. Just kind of excited to talk about global warming. I always enjoy talking about that with you because you have a very balanced approach to it, and I think the more we can have a balanced approach, that it's not we're not going to destroy the planet, but it is something we have to consider. And so I'm interested in the topic we're talking about today because it seems to really bring that balance into it. So I'm going to throw the floor over to you. Kind of, what is the winter gatekeeper hypothesis? How do we get introduced to that?
All right, so it's basically the idea that we're perhaps not accounting fully for what we call meridional heat transport. So south to north, or north to south, depending on which hemisphere you're in.
Mm-hmm.
So the Earth is constantly moving energy around because 2/3 of the energy that falls on half the Earth's surface, the tropics, is moving somewhere. It wants to be doesn't want to be, but the Earth is, heat moves to cooler places. So
you're saying 2/3 of the heat that the 2/3 of the energy that the Earth absorbs is absorbed within 50% of its or 50% of its area,
right,
centered around the tropics. And so rather than the tropics just getting hotter there, that heat moves somewhere across the Earth.
Right, and
that's the idea.
And actually, if this wasn't happening, there would be a 100 C difference between the equator and the poles rather than just a 40 C difference.
Okay. That's 40 C. So that's like roughly 0 to 100 degrees, water boils or freezes at 0 C. 100 degrees Fahrenheit.
Well, I'm just talking about a temperature difference.
I know. I'm just trying to get a scale for what that difference is. That's basically freezing water to a hot day out. That's about 40 degrees C. That's the temperature difference we're talking about.
So I'm kind of a paleoclimate guy. And one of the things that you notice if you study paleoclimates, there's all these different climates that have happened. It hasn't just always been the same as today.
Okay.
So we have what we call a hot house climate and a greenhouse climate, an ice house climate, an extreme ice house climate. And where the modern day climate is a little closer to the ice house climate, actually. But the differences between these climates are, what you see is that at the equator, the average temperature is always somewhere around 25 C.
Okay.
But the polar climate differs dramatically depending on which one of these climate regimes you're in.
Interesting. Okay.
So, for example, in the extreme hothouse climate, maybe we had some of those during some of the dinosaur eras, or right after the Cretaceous. There was a very hot climate around, say, 55 to 60 million years ago.
Okay.
You in some of those extreme cases, you had a polar climate that was 13 C, so only 12 C cooler than the tropics. So you actually had warm weather vegetation in the polar region.
Wow. Okay.
But in the extreme other end, the extreme icehouse climate, you would still have that 25 C at the equator or something close, but you might be minus 50 C at the pole, 75 C less. And this seems to have to do with this meridional heat transport, how well the Earth is moving heat and moisture from the tropics to the poles via the ocean currents and via the atmospheric circulation.
So naively, I would expect, so if you take that hothouse environment where it's 25 C at the equator, 12, 13 C at the poles, that would be more efficient heat transfer going to the poles. And then in the hothouse region, or in the cold house, or where it's, frozen, I would expect there to be less energy transport. Is that correct, or am I?
Well, this leads into what we call the equable climate paradox.
Okay.
Because it seems like when there is less heat being transported to the polar region, or both poles, the Earth gets hotter.
Okay.
And when there's more heat transported to the poles, it gets cooler, which seems somewhat counterintuitive. You would think that overall the planet might be warmer when the heat transport is moving it to the pole, let's say, more efficiently. And a lot of the efficiency has to do with where the continents are and how the oceans are configured, because that affects ocean and atmospheric circulation. So the Eocene climate I mentioned a few moments ago,
That's which one's the Eocene?
that'd be like 55 million plus
okay, so right
years
after
ago.
the dinosaurs. Then.
Yeah, the climate was very warm, but the continents were positioned such that it was most of the water currents were circulating east to west or west to east, staying in the tropical regions and not moving heat out of those regions. That's very different than today.
No, that is interesting. Yeah, because I've seen maps of at least the ocean currents, and they basically go. There's a whole lot of north-south flow in the ocean currents today. So if I get what you're saying, it seems to be in that Eocene, you've got basically currents are just flowing around the globe rather than having a lot of north-south movement.
Yes. So, and I've got a chart for that, but the present-day climate, as you said, is much different. So, so now we have no land mass essentially in the high mid-latitudes in the southern hemisphere. So if you're an atmospheric scientist like me, that you know that in the mid-latitudes you have what are called the westerlies. So you have all these mid-latitude storms that flow around the globe in the westerlies. In both
mid-latitudes being
like 30 to 60.
30 to 60, okay.
Maybe even a little above 60 sometimes.
All right.
That's in both hemispheres. But in the southern hemisphere, there's no land masses in the way. There's no mountain ranges in the way for the most part in what surrounds Antarctica. So you have this very highly developed mid-latitude storm track, basically, and polar vortex and jet stream that is included there. That system actually acts as a global pump for the ocean. The freeze-thaw cycles, which create fresh water, and change the salinity properties, create sinking water there. So Antarctica, or the surrounding areas of Antarctica, are one of the global heat pumps. The other one is in the far North Atlantic. That wasn't there in the Eocene in the same way. So now you have water that goes all around the world that some of which ends up in the North Atlantic, and there it also sinks because of changes in temperature and salinity properties. And so that's sort of the other pump in the northern hemisphere. In fact, you even have, because of the fact that the Atlantic is north-south all the way, through the southern and northern hemisphere, basically, some of the heat in the southern hemisphere is actually transferred to the northern hemisphere and goes through the pump in the North Atlantic.
So by pump, you're just talking about some place where water comes in a certain form. It either gets colder, hotter, more saline, less saline, and as a result, it drops lower, raises higher, and so it causes the water to move, and so it drives it drives these ocean.
It changes the water density by a few percent, and that is enough to start this process. And you could liken it really to a so I have another slide on this. If you think of the ocean and the atmospheric heat pumps as an engine, the tropics would be the engine, and so all that heat's getting dumped in the tropics. The engine's running, and it's pushing the heat out to the radiators. In this case, you have two radiators: the northern polar region, the southern polar region, and the only.
Why are they the radiators?
Well, okay, good question. So we have a greenhouse effect active on the Earth, and that's not just caused by carbon dioxide. It's caused by water vapor, carbon dioxide, methane, ozone, and several greenhouse gases. Water vapor is 75% of the greenhouse effect. Carbon dioxide is probably 19%.
Okay.
Now, most of the non-water vapor greenhouse gases are fairly well distributed in the atmosphere. So that would mean that, in the polar regions, you've got roughly the same amount of carbon dioxide as other places.
Gotcha.
So the effect from them is going to be similar. Now, it's not exactly the same. It may vary by a few percent. But in water vapor's case, water vapor is cycling through the atmosphere. It exists in all 3 states on Earth, and so it evaporates, it condenses in different places, and actually, moist air can transport heat like 100 times more efficiently than dry air, and it actually doubles the atmosphere's heat carrying capacity. So that the presence of water vapor has a lot to do with this winter gatekeeper hypothesis and the ability to transport heat. But in the polar regions, water vapor is like 1 gram per cubic meter in the winter is an average water vapor content, whereas, say, in a tropical region, it could be 20 grams or more. So the water...
Well, you just go look at the Antarctica, and we tend to think of that as very wet or whatever, but it's actually it's got a desert type weather profile. So even though it's got a lot of snow, it doesn't have a lot of water in the atmosphere.
Right.
So it's a little counterintuitive, but so there's less water vapor, which presumably means once the heat gets there, it can funnel off into space more easily because there's not as much greenhouse gas because of the lack of water vapor. Basic idea there.
Exactly. So even you have these other greenhouse gases, because water vapor is such an important part of the greenhouse effect. The fact that it's so scarce in the polar region means that the Earth is able to emit long-wave radiation much more efficiently if heat makes it there.
Okay.
So through the atmosphere, through the ocean, heat is getting transported to the polar regions. Now, it turns out that the Arctic is actually more important than the Antarctic in this regard. Those high mid-latitude regions of the Antarctic are important for that pump, and there is heat emitted there, but because that mid-latitude belt of storm tracks is so efficient, you have a strong jet stream, you have a strong polar vortex, and that actually prevents a lot of that heat from making it all the way to Antarctica.
So it moves efficiently down to, kind of the roaring 40s or what, the place where you got circumpolar or go around the Earth with no land, and that kind of basically serves as a barrier in some
sense. A wall,
sense. Okay.
Yes.
All right.
And so in the northern hemisphere, it's different because you have about 50% land mass, you have all these mountains, you have all this diverse terrain, and so that really interrupts the polar vortex and jet stream a great deal in the northern hemisphere.
Gotcha.
So heat is, generally speaking, transportable in much greater quantities to the Arctic than it is to the Antarctic. It's almost like the Antarctic is this isolated thing. In fact, even the warming that we have seen, let's say over the last century, Antarctica really hasn't warmed that much. In fact, in many of the last several decades, it hasn't warmed at all. And I think it's related to this effect.
So is this the sort of thing we can actually measure the amount of heat flow going off the poles? I mean, I know we can measure temperatures there. Is that a measurable thing, or is it an implication of we know what the temperature is, we know the atmospheric composition, and so we can calculate how much heat's coming out?
It is measurable, but I would say that at the top of the atmosphere, the error bar is about as large as the number that we're trying to measure. But for example, let's take the last 25 or so years. There was a climate shift of some sort about 1997.
Okay.
And after that time, the meridional heat transport to the Arctic increased quite a bit.
Okay.
And I actually have a chart showing that, and you can see that the Arctic temperature went up several degrees on average, along with the emission of heat.
Okay.
So we're probably talking about an extra, 8 watts per meter squared in the winter and maybe 4 in the summer. The imbalance that's often thrown around due to global warming is somewhere in the neighborhood of like 2 watts, 2 plus
Okay.
watts. So that's a significant amount of energy. The Arctic is, maybe 10% of the globe, but if you can get the heat there, you're going to lose a lot of heat to space because of the weaker greenhouse effect.
Okay, so if I get what you're saying, we've got energy coming onto the earth or coming into the earth. Most of it's being absorbed in the tropics. That we're also so now that heat is being moved around, and how it moves around affects the temperature or the global temperature of the earth. That as heat is efficiently moved up to the Arctic in this case, because there seems to be a pretty good barrier to getting into the Antarctic region right now, that it's going to warm up the Arctic region, but in doing so, that's a symptom of the fact that more heat's going there and escaping out into space. So in essence, the warming of the Arctic region is a reflection of the globe cooling because it's funneling more heat off through the poles.
If you keep this process going for a long period of time, then it can actually cool down the planet, even though the Arctic is warmer in the short term, and that's the paradox.
Okay.
Because if this process continues for, let's say, a few centuries, the Earth can actually get cooler. Now, this happened on a grand scale, in the last ice age, because the ice age cycle is driven largely by obliquity, by the tilt of the Earth, and it essentially creates some process like this that goes on for centuries and centuries, and eventually the Earth gets cooler. And in fact, when the ice age cycle started about 2.5 million years ago, it seemed like they followed the obliquity cycle very regularly, about 40,000 years. But then at some point, they started skipping obliquity cycles. And what happened is all of this cooling over long periods of time made the Earth's background temperature cool enough that coming out of an obliquity cycle wasn't enough to jump us out of the ice age.
Oh, okay.
So then it started to where it would take 2 or 3 obliquity cycles. So
Interesting.
the last cycle took 3 cycles, 3 obliquity cycles to jump out. But
there's an interesting part because in discussions of global warming, one of the things that's often talked about is we go look at the poles and they're getting warmer. That means the globe is getting warmer. But it seems like and that's a function of we're putting more greenhouse gases up there. In some sense, do the greenhouse gases affect the transfer? Because it seems like if what you're saying is correct, this winter gatekeeper hypothesis, that as the as the transfer from the tropics to the polar region increases, the temperature of the poles are going to increase, but that actually over long enough time is actually cooling the planet.
Including the Arctic.
Right.
Yes.
And so it seems there is the fact that the poles are getting warmer, is that because we're making the planet warmer through greenhouse gases, or is that a sign that this meridional transport is getting more effective? And is that driven by human activity or not?
Well,
or is
at
this
least
the question
at least on a short term, or maybe even as long as century scales, it could be either.
Okay.
I mean, so we had what's called the Little Ice Age, and it started, let's say, around the 1300s, and really we didn't come out of it till the 1800s.
Okay.
And the Little Ice Age, from a paleoclimate perspective, we know that the sun is having an effect. Now, the whole debate is about how can the sun be having an effect when it doesn't seem to vary that much. I'll get into that in a minute. But essentially, over long periods of time, the solar cycles went to a very low period of activity. What's called the Maunder minimum is one of those maybe 70, 80-year periods where there's very few sunspots and solar maximums were very, very weak.
Right.
And what happens in a solar maximum, or rather a solar minimum, and especially an extended one like that, if you just have a solar minimum like a normal solar minimum, 11-year cycle, you're just at solar minimum for maybe a couple of years. And what that does is it essentially produces less UV radiation into the stratosphere.
Okay.
Overall, solar radiation only varies like 0.1% between a solar cycle, and that's why a lot of people have said, well, how can this affect climate?
Right.
But yet, as a paleoclimate person, we know it affects climate. There are these 2,500-year cycles, Bray cycles, and eddy cycles, roughly 1,000 years, and then even some shorter ones. And a lot of these appear to have converged in the last little ice age. And they're actually, if you go back through the Holocene, you can see other ones that happened at roughly 2,500-year intervals.
Okay.
And cooled the planet by maybe 0.6 C or something.
Okay.
And it probably more pronounced in the northern hemisphere. But it appears that this process, the winter gatekeeper hypothesis, is what's causing this. Because over long periods of time, if you continue to have solar minimums, it weakens the polar vortex, it weakens the mid-latitude jet streams to where that transport of heat is happening more readily to the Arctic. And so even though it warms up the Arctic in the short term, over a long period of time, it actually cools the Arctic and the planet.
And long period of time being a century, few centuries?
Several decades to
Several
a century
decades to
or
a
more.
century. Okay.
Yeah. So, and maybe one of the reasons, in fact, not maybe, but I think one of the reasons is that this hasn't been real obvious is, and I've got a slide that shows what happens with the vortex in low solar activity. So you get a weak wavy vortex, especially in the northern hemisphere, because as I said, the southern one is pretty much a solid wall. The heat transport increases to the Arctic, starts emitting more heat into space. So overall, the planet is cooling through its northern radiator, if you want to call it that. But there are other factors in the climate system that can interfere with this and either enhance it or reduce the effect. That and why this is happening is really mostly related to the stratosphere. The stratosphere is a very small percentage of the Earth's atmosphere in terms of mass, but it contains almost all the Earth's ozone, which is 4% of the greenhouse effect. And during a solar minimum to maximum range, you can get like 30 times the variation that you get just from looking at, say, the overall 0.1% radiation change.
Okay.
So that has a huge impact, and it has to do with how much ozone is getting created, because this can change, at least in the Arctic, it can change the solar, the stratospheric temperature by 10 C.
Wow, okay.
So the effect is stratospheric, and there's a couple of patterns in the stratosphere that affect this. There's one called the quasi-biennial oscillation, and it's ultimately driven by convection in the tropics, by storms in the tropics. But it's a cycle that happens, has about a 28-month period, and it changes from an east wind to a west wind.
Okay.
And when the wind is east, then it can actually enhance the movement of heat to the polar region during a weak solar period. But if it's westerly, it can actually work against that. And it just alternates back and forth. And then there's also El Niño, or what scientists call INSO, which stands for El Niño Southern Oscillations. Essentially, what that is there's normally a big warm pool of warm water in the western Pacific, and when that warm pool gets too large, you get a shift in the water toward the east, which we call El Niño. That causes a significant pattern change to climate all over the world, really, especially in the tropics, but even the extratropics outside in mid-latitudes. It can affect areas of drought, areas of high precipitation. It can change tropical cyclone tracks. It changes the trade winds in the tropics, and all of this changes the climate. So normally El Nino, I've always, as a person who's kept track of climate in the eastern U.S. for many years, I always know El Nino years is, it's going to warm up about 1°C,
right?
Depending on the strength of the El Nino. But that's just the short-term effect. The El Nino is actually, it appears that what's happening is actually part of this global transport system of heat. So when too much heat builds up in the tropics, the El Nino happens, and that actually helps. Heat gets transported away from the tropics as a result. So in the long term, it could actually help cool the planet because it's transporting that heat to the Arctic.
So let me ask, if you don't mind, it sounds to me, and there are pretty significant implications of this idea to how we think about global warming. And, you kind of have two general positions. One is global warming is kind of a hoax. It's not really that big a deal. We don't have to worry too much about it. That's one extreme end. The other extreme end of the scale is we're going to destroy the planet if we don't take care of this. But in that picture of global warming, at least the way it's often presented in my hearing, is that, we're putting greenhouse gases up into the atmosphere. We know that greenhouse gases absorb more radiation, so the planet is warming, and that's what's going on. And we see evidence of the tropics getting warmer. We see evidence of poles getting warmer. Glaciers are receding, all of these things going on. That the tie is because we're producing more greenhouse gases, it's causing all these effects. Is it possible that the effects we're measuring are really not related to the greenhouse gases primarily, but more related to the effects of these meridional transport, things that move heat from the poles or from the equator to the poles more readily?
Well, there's a balance there. I mean, there's been a general upward trend, but in temperature, but a lot, at least a part of that temperature trend can be explained by this process. So for example, coming out of the Little Ice Age, which is one of those large solar cycles, you would expect about a 0.5 degree C warming coming out of it. And that's essentially what we saw from 1850 to 1950.
Okay.
Then we saw a slight cooling, which has been difficult for models to reproduce. And why did that happen? Well, this actually explains that, because what we're seeing is, so what I haven't mentioned is there are these multi-decadal oscillations in like sea surface temperature and patterns. One of them is called the Pacific Decadal Oscillation, or PDO. You could think of it almost as sort of a long-term El Nino pattern. Then there's the Atlantic multi-decadal oscillation. The PDO might have a cycle of about 40 to 60 years. The AMO, the Atlantic multi-decadal oscillation, maybe 60 to 80. And then you've got El Nino, which is maybe 2 to 7 years.
Okay.
All of these things appear to be related to oscillations in this meridional heat transport. So this is sort of like superimposed on top of whatever's happening with the background greenhouse gases.
Right, okay.
So for example, in 1997, there was some sort of a climate shift. And there seems to be, like every 2 or 3  11-year solar cycles, some sort of a climate shift. We had one
every 20 to 30 years, roughly.
Yeah. We had one in 45. We had one in 76 or 77. We had one around 97, 98.
Right.
And after the 97, 98 shift, the climate didn't continue to warm little, if any, at all. And so after about 15 years, people started calling it the pause, and it wasn't really predicted by the climate models.
Okay.
But when you recognize that this is going on, so I mentioned earlier about after this 97 shift, the Arctic started warming up dramatically, and there was all this extra emission of heat from the Arctic.
Right.
Well, this explains that, because the cycle shifted to where we had more meridional heat transport during that time. Now, chances are it's going to shift again at some point. The AMO is in a warm phase right now. It has been since the mid-90s. If it goes into a negative phase, which, based on past experience, it probably will sometime in the 2030s, that may slow down the warming again.
Mm-hmm.
And it may have an effect on the change in transport.
Mm-hmm.
When the solar maximum occurs, and we're actually in one right now, but when solar maximum occurs, if these other factors like the quasi-biennial oscillation, El Niño,
Mm-hmm.
and even volcanic effects sometimes, depending on whether they're working with it or against it,
Mm-hmm.
then it makes it results in the polar vortex jet stream to be stronger. Therefore, it cuts off a lot of that northward transport.
Right.
And therefore, the planet begins to heat up as a whole, even though the Arctic might get cooler at that time because it's being protected, kind of like the Antarctic.
Right.
But that heat has nowhere to go.
So this is not a snarky question at all, but are these sorts of effects included in the climate models that the IPCC uses? Are they? I can't imagine they're not included at some level. Are they included well, or what? I mean, how? What's your assessment there?
There's not much mention of it in the last climate report, the AR6.
Okay.
Maybe one mention. My understanding is that there's a lot of variety between what the models predict on this. So I would say they're not modeling it well.
Okay.
And that's probably part of the reason, because essentially we're assuming here that all of this transport of heat kind of balances out around the globe, and this doesn't appear to be the case, because if you get it in the right place, it's going to escape more easily.
Gotcha. So, again, looking at our two camps, one says global warming's a hoax or doesn't happen. This seems to add evidence to that position that scientists haven't gotten the natural effects proper. When you do that we can explain a lot of these things that people are using to argue for global warming. How would you respond to someone making that argument to you?
Well, I wouldn't go so far as to say that it's all natural effects. It's certainly not. I mean, these natural effects can explain some of it. But, I would be, for example, the last 45 years, since about 1980, right after that 76 climate shift, the world began to warm pretty dramatically from, especially the 20 years from, say, about the late 70s to late 90s.
Right.
But that was during the time when the polar vortex was stronger and the heat wasn't efficiently going to the Arctic. And so naturally, in that case, you've got perhaps man-made global effects being accentuated by the natural effects.
Gotcha.
Whereas after 97, it was the reverse. The natural was working against it. So, it's really a combination. And what I notice is people who let's say are on the more alarmist side, they will essentially almost completely downplay the natural variations.
Okay.
And then people on the other side will talk about the natural variations but downplay anything else. And I really think there's room for both here. There's the climate system is very complex. You've got.
Well, and I would state it even a little more strongly. Not only is there room for both, if we don't account for both, we're just missing the picture. Yeah, I've always asked, when people ask me about climate warming or global warming, I kind of say there's four questions. Is the globe getting warmer? Data seems pretty obvious that it was, and it has been. Are humans involved? And the question is yes. You're kind of, and as I hear what you're talking about here, what you've been saying all along is yes, humans are involved. We're not all the cause, but we're not none of the cause either. And so it's where is maybe a little bit open for discussion, but clearly both of them. But if you don't get those two questions right, how big a deal and what do you do about it, you just miss. Because if you neglect the human causes, which the global warming's a hoax camp would tend to do, you're going to miss that there are things humans are doing, and you're not going to mitigate that. Whereas if you say, well, you neglect all the natural causes, you're going to get the wrong solution and cause damage as well.
And I'm not going to stand here and say I've got it all figured out about how much is human and how much is natural. But as an estimate, there are some scientists who have said that the AMO could explain, 0.3 C of the warming since 1980.
Which how much warming has there been since 1980?
Probably 0.8, 0.7.
So not quite half of it.
Yeah.
Something like that. Okay.
And at different times, back, like I said, in the early 20th century, when you had the half C warming, that's probably almost all natural because, the greenhouse issues weren't really that of great concern at that point.
Right.
But we need to keep studying this because, there's a lot of uncertainty here, and we don't need to throw out something just because it meets a certain agenda.
Right.
And I think the other thing I'd want to add in here too is that it's not all about carbon dioxide. It's not all about greenhouse gases even. There's other factors, urban heat islands, for example. I've studied that some, and even small cities, you can have like a 1C change in temperature under the right weather conditions, warming effect. If you're in a large city like Atlanta or London or something, it could be 8 or 10 C. Now, there's certain weather conditions where there's almost no urban effect, and then there's other weather conditions where it's very pronounced. I would imagine on a day like today, it'd be pretty announced here in LA. So that's a man-made effect, but it has nothing to do with greenhouse gases directly. Maybe so the way you need to address that is totally different. Maybe you put more reflectivity on your building or something, but we've got to realize this is a very complex issue, and I really think, if I may say so, that a lot of times people who have a certain view of warming, whether it's man-made or not, it really has more to do with they're concerned that someone might be using it for an agenda or something like that, and maybe they are, but it doesn't change the facts of whatever the science are one way or the other.
Right. Well, I think that's a pretty profound point. I'm curious. We're about ready to wrap up here, but it does seem to me that in most of my discussions with people, my sense is I could largely predict their position based on their political leanings, which all that says is that we think about climate change through a political lens. It does seem to me that if you step back and look at it through a scientific and even theological lens, you get a very different conversation out of it. I think a conversation where you can actually make some real change, where you're going to be helping take care of the planet and the people who live on the planet at the same time. So, any final thoughts here before we wrap up?
Well, I just think this is a really fascinating hypothesis, and I think one of the reasons that it was discovered, actually it wasn't, there's some great books out there actually on this, but actually a meteorologist by the name of Karen Libitsky is actually the person who discovered this. She's been passed away for about a decade, but so this is not a brand new thing. It's fairly new to me, but I think it answers a lot of questions, and I think it just illustrates that we need to really think through these issues and really understand that we're dealing with a very complex thing here. And I've probably been a scientist for 35 years, and over and over again, you discover something, and then 5 or 10 years later, oh, wow, this really changes the perspective. It's not like you threw everything out, but it really hones in your understanding, and that's what science does. It continues to hopefully draw us closer and closer to what the truth of the climate system is in this case.
Well, thanks, Kevin. I really appreciate your comments. And I want to thank you for joining us today on Stars, Cells, and God. I want to encourage you to join the discussion in the comments below. Like this video and subscribe for more content. We actually drop new episodes of Stars, Cells, and God each Wednesday. You can get them here on YouTube or on your favorite podcast app. I want to encourage you to share this video and have a good conversation with a friend about it. And remember, the more we know about science, the more reasons we have to believe.